All right.
It's official.
All right. What's your question?
So let's see. I'm working on a 1D motion with position function. Would you like me to just show it to you? Does that make it easy?
Yeah, that might make it easier.
Cool. Um, it's this here.
Ah, okay. Object, so they give us the equation, okay. At some point, the object changes from moving in the positive to the negative. At this instant, the object's position is x1. Okay, now I think I'm learning how to read these because there's not a question mark there, but you're trying to find this x1?
Yeah, that's essentially how it usually goes.
Okay, all right. Maybe I'll start by asking you, have you done anything on this, or should I jump right in?
Yeah, I mean, I know that I need to be doing a derivative, I think.
Oh, okay, wait, okay. So why?
Because this is where I get a little bit, the units are kind of screwing with me, is because I see I've got seconds cubed and seconds squared in the bottom, and I don't know what meters per second cubed is.
Okay, okay, good. I'm kind of hearing two questions here. I'll start with your second one here, the units. Don't let that bother you too much. If you look in the equation, for example, the first term. No, let's go to the second term. The second term says minus bt cubed.
Mm-hmm.
That whole term, all the units together need to come out to be meters. Yeah, exactly what you're circling right there.
Yeah.
Yeah, all those need to come out to be meter. And so it's time cubed. So we know we would get seconds cubed from the t cubed. So that means the other units, and they don't really have a physical meaning, need to be time cubed in the denominator, so they cancel off, and a meter in the numerator, so that when the b and the t cubed are put together, you'll be left with just meters.
Okay.
Yeah, so the fact that the units for b is meters per second cubed is just the necessity for the units to work outright to be a meter, because the equation actually says what's position.
Okay.
So don't try to interpret anything with those units. Those are just the necessary units given the equation.
To make things, okay, got it.
And you can see the same thing in the first term, the a, because it's a t squared. So
yeah, the seconds match the exponent.
Right. And so the a has to have a second squared in the denominator with a meter in the numerator. And even though it has units of acceleration, that has nothing to do with acceleration.
Okay, that was what was sort of tripping me up, was I was thinking, why do I have acceleration in some sort of form that I don't understand?
Right. And I suppose it even has an a in front, and all the more reason you might think acceleration, although we usually use a lowercase for that. All right, so that's kind of the second question I was hearing from you. But going back to your first question was, you said, I think I need to take a derivative. And so your gut was telling you, right, you do need to take a derivative. But I wanted to expand on that, because here is where these physics problems get challenging. And maybe you even remember, maybe even still have it, but I would assume not. Students in your math class where they would be given a word problem and they would just kind of cringe, and I'm kind of thinking like a high school algebra class, and the whole problem set says solve for x, and then the last two at the bottom are those dreaded word problems.
Mm-hmm.
Oh, and everybody moans, oh, don't give me a word problem. And the reason people have difficulties with that is it is hard. It is hard to take the words and change that into math, let alone then the next step and do the math.
Mm-hmm.
But see, in a physics, that for better or worse, every problem is a word problem. And so you've got to read the words and okay, how does those words get translated into an equation? You know, how can I use that? How can I go from words to equations and then eventually solve the equations? So as I was kind of saying on our last session, which I forgot to hit the record button, that, oh, by the way, does this have a number? I thought I'd be a little more, pay a little more attention. So when I post the Zoom recording, I could say what ones were done in what
We don't
session.
particularly have numbers, but like this thing at the top, 1D motion with position function, is what the problem is labeled as in our homework system.
Okay, I'm gonna try to remember every time I do a problem today and in the future to write that down, so that'll give students a little bit of direction other than here's a Zoom session.
Totally.
Yeah, but I think students have gotten pretty good at kind of scanning it, and they'll see something like this, and if they're in 121, stop. If they're in 122, go, okay, that's not for me.
Yeah.
Okay, because that's kind of what I did. I don't know if we were face to face, we really kind of have a block. We have the first day on Friday, the first part really for 121 people, and the next for the 122 people.
Yeah, that's sort of, I actually thought about making that suggestion to you, but I just didn't know if, I assumed you're probably doing it this way just so that you don't know what people's schedules are with the sort of asynchronous nature of the class, and you want people to be able to stop in whenever they need to ask a question.
Yeah, and that's why I started it that way. I mean, if it got odd, I was going to make a second step, and I don't think I'm there yet. It kind of depends how this goes. But I might do something like priority during these hours will be 121. So if you come in and put something in the chat, I'll go right to yours.
Yeah, that's like exactly the thought that I had for possibly streamlining it and making it a little, so that people from 121 can know that if they come at a time, it's mostly going to be work on their thing, just like, giving priority. And then if nobody from that has a question, somebody else can jump in, or if somebody, can only make that time, you squeeze them in or something, but
yeah, and I even went further. I've invited all the 102 people to come too. It's not normally for that, but I said, hey, just come along here, and usually their questions are pretty short.
Yeah.
Okay. So what I was getting at in that is that and like I said, your gut is telling you something about a derivative, and that's the key here, because and here's how I read it. It says, at some point, the object changes from, let's see, moving in the positive direction to the negative direction. All right. So that phrase, moving in a direction, is really the velocity. They're saying, okay, it has a velocity that is now positive, and then the velocity now becomes negative. Okay. And that right then tells me that the information they gave me is related to velocity, yet the equation I have is an equation for position. So how do I change an equation of position into an equation of velocity? I take the derivative. Okay. So, and that's what, your gut was telling you. And I think that was what was going on in your head, maybe indirectly. I don't know if you articulated it in your head, that well, saying, oh, I see a movement. That's a velocity. I see a positive to a negative. I need a velocity, and I have position, so I got to take the derivative. All right. So, and I won't take away your sharing screen, but I'm going to take that derivative on my piece of paper.
Yeah, here. Well, I put mine down. Or do you need to see that again?
Yeah, put that back up. Okay. Because then if you took the derivative, you would have gotten, let's see, a 2AT minus, oh good, it's back, minus a 3BT squared, right?
And you'd call that V of T, yeah?
Yeah, and so that's V of T. A lot of times I just write V just to try to keep things a little simple. But implied in there is V of T. Now, here's another part when I'm reading this, right? It goes from positive to negative. So anything that's going from positive to negative would then be crossing zero.
Yeah, so that was my thought, was that I needed to find zero somehow, because
Yeah.
that's when it's switching from positive to negative.
Right. So I'm gonna take that equation we just said and set it equal to zero.
Okay.
Okay. All right. Now maybe I'll go ahead. This will give me first time here today. Let me get my camera ready.
Mm-hmm.
Switch over. All right, and then with my, here we go, camera. All right. I've been liking this camera idea. I hope it's working for you guys.
Yeah, it works. It works fine.
Yeah, it was like.
When they sent everything online, just went and got myself like an iPad Pro with the with the Apple Pencil, and
Yeah.
I've really learned to love it. It's got all these neat features that, for someone with a little bit of OCD like me that likes to have all their lines, it'll straighten all my lines for me, and it'll like, oh, it's beautiful.
Good. Yeah, I looked at that too, and I go, oh, that was pricey. But I did see I could buy a pen to write on my touch screen on my laptop, and so I did that, and I've done that a few times with people. But I've really just been finding the camera on the piece of paper just very useful. Yeah.
Totally. Simplicity is.
Yeah, yeah. I think we got with so many changes. Simplicity. That's why, at least for my classes, I know that you're in a different class, but for mine, I'm like, okay, look, why don't we just take the test the old-fashioned way and scan it and send it up to Canvas? So the only new thing is figuring out how to scan it and put it in PDF.
Yeah, that's why I got this iPad, because I can just write it all on my iPad and then just like on my app, and then just it's already a PDF and I just send it out.
Right. Good. Okay, so back to this problem. So now I think you're beginning to understand the logic of why, number one, we took a derivative to get the velocity, and then number two, we're setting it equal to zero.
Yeah.
So here's where the math kicks in. Let's see, if I factor out a time, I get 2a minus 3bt equals to 0. And then, like I said, this is the part where now we've gone to actually doing the math, not just reading it and what the words mean, but now we're solving this. And so one option is t equals to 0. Another option is 2a minus 3bt equals to 0.
Mm-hmm.
And so there's going to be two answers here, but I suspect that one of them is going from negative to positive, and the other one is positive to negative. I'll say why in just a second. I've got some more math to do, but let me solve this. So this would be 2a equaling 3bt, or t is 2a over 3b.
Mm-hmm.
And so if I can get a number, this would be 2 times a. Oh, I forgot to write down a. What was a?
A is 7.86.
7.86.
And
then
B is
by
5.7.
And then say that again. What?
B is 5.7.
5.7. Okay. All right. So I got a 0.919 seconds. All right, so technically there is where the speed is equal to 0. Okay.
Mm-hmm.
Now the question is one or even both of those fitting the condition from positive to negative? And there's a couple ways we could do this. This is one way that comes into my mind. It goes back to algebra instead of calculus, but we could do it with calculus. Is the original equation, which I guess I didn't actually write down. Let me write it down now. That was an AT squared minus BT cubed. But see, it's cubic. And so a cubic equation, let's say, oh, I apologize. I put the wrong symbols on the graph.
Mm-hmm.
If you study this math, when time is really, really large, of course, you cube it, it's really, really large, but it's got a negative in front of it. So this is going to shoot down to negative infinity for large times.
Mm-hmm.
And for negative times, right here, negative times, we'd be a very big negative, then with a negative in front of it, make it positive. So I have a graph, that looks something like that. Has that standard cubic equation where it's got two little humps in it.
Yeah.
Okay. Now, I didn't draw mine really well because I already solved where the roots are. So maybe I'll draw a better picture here. So here's my graph, X and T. And I know it goes through T equals to 0 and about a 1. And I know it's up here for negative time. So it must swoop down, come back up. Oh, shoot. No. That's when the velocity is 0. Let me try that again. I started to draw that as if that's when the times were equal to, the position was equal to 0. Let me try that again. All right, I do want to plot position versus time, okay? So coming back to this graph, when the velocity equals to 0, that's the slope. So this point and this point. So this point must be at 0 time, and this point must be at 0.
Okay.
And maybe, I don't know, maybe this wasn't such a good way to go, but I could also see in the equation that when time equals to 0, the position equals to 0. So this graph must come down and do this. Then it must arch up and do that. So this point here.
Your camera just froze.
Oh, you know what it is? I think yep, it's first time we used it today here. Let me change the settings to never go to
sleep.
Yeah, never. Okay. All right. All right. So, this slope right here would be 0.919, and this point here would be the 0.
Okay.
Okay. So the question said, when does it go positive to negative? And so we are looking at a slope going up, which is positive, and then a slope going negative, which would be here at this one. Whereas this one, the speed, would be the slope. So that would be a negative going positive.
Okay.
So that's that doesn't fit what they want in the problem. They want the one that goes from positive to
negative.
In fact, now that I did all that, I probably would have been better off and easier for you to see. So I'm going to do it again, but plot velocity versus time.
Okay.
Number one, I think you're probably, most students anyways, I don't know about you, but most students are a little stronger with parabolas, and that's what this is. This is a time squared.
Mm-hmm.
And with the negative in front means it's concave down.
Yeah, that makes sense.
So, and we solved for the zeros. So this would have been
So the zeros of the parabola are at point are at 0 and 9.19.
Yeah. And so it would have looked like this. And
yeah.
I should have just done that one.
Okay.
Well, maybe it was a good exercise to talk about the position.
Yeah.
But there it is in this graph of velocity. You can see that at this point here, the 0.919, not the 0, is the one that goes from positive down to negative.
Gotcha.
Now, to finish this problem, if I remember right, didn't it say find the position? Not the time. So we still got some more work to do.
Yeah, so it says at this instant the object's position is x1. So my thought there would be we found the time.
Perfect.
And you plug that back into your original x of t equation.
Yeah.
And that would give you the position.
Right, exactly.
Okay, cool. Yeah, I need to get a little more comfortable with thinking about these things graphically. I've gotten pretty far in my sort of mathematical equations, so I always just, I want to think about everything mathematically, and it's a little thinking about it in the real world is a adjustment for me right now.
Yeah, if there's any advice I can give you is, and maybe it's so obvious it's not very good advice, but it's not easy to do, is that all these numbers, equations, they have a meaning, and so you want to be able to not just do the math but read the math.
Yeah, I think it's just for me. I'm a very just do a bunch of them, and eventually my brain starts to sort of log it all back here in the sort of long-term memory, and it all starts to just make sense. But
yeah, that's very true. Very, very true. Because and that's why the typical way, both traditional and I really don't see a better way of really learning this, is just this repetitiveness of doing problem after problem after problem. And I even tell students that when I give a homework assignment, it has quite a few of them. But here's the neat thing about long homework problems is they're what I call self-correcting. And what I mean by that is if you don't fully understand them, the problems take you a long time. And because of that, you spend a lot of time studying it. Mm-hmm. But as you get to learn it and you know what's going on, they only take you a short amount of time, which it should. If you know it, you shouldn't have to spend a lot of time on it. So maybe that'll occur halfway through. For some people, you can go through a whole assignment and you still haven't completely got a full understanding of it. And in that case, I would say you might even want to do quite a few more problems, even though they weren't assigned, but get yourself ready for the test.
Totally. How are you
Yeah.
guys? I'm just curious. How are you guys running your how many exams are you having in like 122 and such? Because we're just doing like a weekly quiz and then a final. You know, we don't.
I noticed that Doug changed that the traditional way, and I stuck. As you pointed out a few moments ago, all of this online stuff is not just new to you students, but new to us teachers.
Yeah.
And the traditional way, and the way Doug had it set up last semester too, was 3 exams throughout the semester, and then a final exam. We went through a bunch of training classes this summer, and one of the things that they emphasized in the training classes were to try to do smaller, lower stake problems. And so Doug's answer to that was he took away all the exams, and I think he's just doing these weekly quizzes now.
Mm-hmm. Yeah.
I didn't do that. I wanted to stick to the traditional tests, and my low key stuff is the homework, where I'm just having them, do a homework assignment each week, and I'm just going to give them credit for effort, and say, okay, you get 100% effort for just trying, and
Yeah.
keep doing that. But we'll have the traditional go 5 weeks, take an exam, go 5 weeks, take an exam, go 5 weeks, take an exam.
Yeah.
So,
I think everyone's learning. I did the two. I did summer one. I did linear algebra and multivariable calc summer 1 and summer 2.
okay.
And I thought I took them with Gabe Pertel, and I thought he did a pretty good job of sort of. He made it so there were more examinations, but they were still examinations, and they were slightly. So we took like we took 6 exams, I think, over the course of the entire thing,
Okay.
a final in 2 parts, but every exam was weighted evenly. And I thought that was a nice mix of, I find sometimes that when something I've just found at City College, because I'm a little older than a lot of the students here, and I'm very committed to working really hard and doing well. And I find sometimes it seems like professors here, because it's a city college and the students that are coming in maybe aren't the best students, they're sort of taking this approach of trying to lift the like lower common denominator students, and lift those students up and make sure that they're keeping up and assigning a lot of what I would almost deem busy work to someone who's committed to learning it, and
Yeah.
so I understand the method of wanting, wanting to get these students who maybe haven't been stellar students their whole lives and bring them up to speed. But for someone who's, really is an adult and is working really hard and works and has a job outside of it, sometimes that busy work can be frustrating. But I've found too, the further up I've gone in the mathematics stuff, that has also dipped down. It's most of the students that I'm in classes with these days are really smart.
Yeah. I totally agree with your observation. That's been my observation. But I put it in this term also, that as a community college, we're kind of the middle ground between the high school and the university.
Yeah.
And so students and teachers who are kind of at the beginning of their community college education, those teachers are like what you were saying. They kind of treat it more as a high school. Here, let me hold your hand. Let me give you busy work. Let me do these. Maybe I'll call it less than adult type of assignment.
Mm-hmm.
And then Then you see the flip side begin to occur on the other end of the spectrum, and that's where you're getting you're getting now. And the classes I teach, the 122, the 123, these are the last two of your classes as you get to transfer to the university. So I like to think my classes need to be more focused on what is going to happen at the university, not what is happening at the high school. So I constantly see that when we have faculty meetings and stuff. I remember one where these two faculty members were politely disagreeing because one was saying, no, what you're doing is a bunch of hand holding. What you're doing is busy work. What you're doing is just, and the word they kept using was hand holding and saying, look, and then the other faculty member was, kind of go, well, what's wrong with hand holding? What's wrong with showing them through? And I sat back and I watched it and I go, okay, now see, that faculty member is teaching the last of the math sequence, the 220. And their thoughts are really university level.
Yeah.
And the other faculty member taught English, and she even taught kind of this remedial English that, it would be an English class you would take maybe as a freshman or sophomore in high school.
Yeah.
And she kept thinking how important that was. And I was like, well, these two are on, 4 years apart in
very different ends of the spectrum.
Yeah. One is talking about a sophomore in high school, and the other is talking about a sophomore in college.
Yeah.
So it made me kind of lighten up and go, you know what? Yeah, where do I want to be? And so I like to be more at the university side than the high school side in our bridge.
I appreciate that. Yeah. I've actually really been enjoying watching your lectures. I'm bummed that I don't get to be there in person to take them because they're engaging. You do a good job of it.
Okay. Good, thanks.
Even for watching them online, even your intro one about units and how to think about physics, it got me all pumped up.
Okay. Good.
Cool. So I'm gonna keep working on this stuff. I'm sure you'll see me again.
All right. Looking forward to it.
Thank you.
Mm-hmm. Because then I'm going to try to write down, I was thinking last week that I should write down which problem students are asking so I could maybe give you guys, when I send the videos, guidance of which ones did we cover. So
I'm going to ask first 32B.
32B. Yep. Okay. Wait, what chapter?
25.
Okay.
This chapter, yes.
Good. Chapter 25. Number 32, and then you're asking B. I'll just put a 32 there, but so chapter 25, number 32. I'll put on my little notes there. Okay. And that's actually really good. The reason I asked you which chapter you're on is because I don't know how many, but there are still people working in 24. And so if if you're actually in 25, which you're supposed to be, you're doing well. So keep that up. All right. So let me go to the questions. And I have, so that's 23, 24. Let's go down here to 25. You're the first one from Physics 122. Okay, so number 32. Oh, yeah. These are the equipotentials. And I don't know if you've done the lab this week. Maybe I'll just ask. Have you done the lab this week? Okay, so So this is connected to that because it
Yeah.
says, here's the figure, here's the equipotential lines. And so if I could roughly draw that picture. Oh, hey, you know what I'm going to do? Give me an excuse to. This one might be better using my screen grab here.
Mm.
So let me try the following. I'll start with grabbing your textbook and grab that picture. 32, you say. There it is. Maybe I'll make it a little bigger, but I think once I grab it, that probably doesn't matter. Okay, so I think I did this last week. I did it the week before. So let me, oops, I messed up. Wrong page. Okay. I probably bumped it. All right. All right. So I'm going to grab the figure so we can talk about the figure. I'm going to go over here to my whiteboard. Oh, maybe I got to go to Zoom and share my whiteboard first. I'm on the camera. All right. So I don't want that. Cancel that. Wait. Okay. Wait. Okay. All right. So what was I doing? Oh, I want to go to the meeting so I can share it. That's where I got myself confused. All right. So here I'm at the meeting. Where did the share stuff go? It's up here. Share. Okay. So share and the Microsoft whiteboard. Well, forgive me. Maybe I'll get better at this. All right. So is it sharing? I'll go to my other screen to see what are you looking at.
I'm looking at the
Oh, good.
integral of e.dA equals.
Oh, yeah. Okay, so we'll ignore that. That's for something else here. But at least I got my whiteboard on there. Okay, so let me just get that out of the way and do a paste. There we go.
Oh yeah, there we go.
Okay, so this is the problem at hand. And it says, find that electric field here. And so one of the things that you hopefully got was that the electric field would be perpendicular to the equipotentials.
Yeah.
So if I were to draw the electric field, maybe, this will be another challenge for me. Got a yellow marker here, but I'm pretty sure, if I remember right, your author does electric fields in orange or kind of a burnt orange. Yeah.
Mm-hmm.
And so I'm going to draw on the screen what I would kind of predict what the electric fields would look like. Okay, does that make sense? I'm drawing a bunch of lines here. Ooh, I like this. Electric field, it's kind of hard to write, but arrowhead. All right, so there's kind of what the electric field would look like. Okay, now its strength would be, how does the voltage change per meter? Now, maybe I cut away from the problem a little too quickly. Doesn't they say each square, let me come back, is 1 centimeter? Yeah.
Yeah.
1 centimeter. So right here at point A, let me go to my black marker and circle point A. Right there. then if you look to the line above A, that equipotential is a 2. The equipotential that point A is actually on is a 4. And the one underneath it is a 6. So from here to here, I'll just kind of color it in black. That's 1 centimeter. And it's a change from a 2 to a 6. So it's 4 volts. So mathematically, I would do this. Electric field is how the voltage changes with distance. So I would say it's 4 volts in 1 centimeter. Now, if I do my units, this would be
the problem asks for for the electric field on B.
Oh, B. My bad. Yeah. I thought it said both A and B. Okay, well,
aren't you doing it the same way they did it in the solutions? Hold on just a second. I think because the solutions has a 4 in the numerator.
Okay, so let me go to B. All right, so let me draw B here. But they're kind of doing the same thing at B. They're saying, okay, if you go to the equipotential before and after, so that's a 2.
Oh, I see.
Okay. So the electric field at B, maybe I should put at A up here and at B here. So the change in voltage is still 4 volts. But now you're looking at a distance of maybe about 2 blocks, because it's about the middle of that one to the middle of that one.
Mm-hmm. Which so is 0.02 meters, right? Yeah, 2 centimeters.
Yeah. Right, and so that's a 2, and then the centa is 100, and so 200 volts per meter.
Yeah.
Yeah. Is that the answer I got?
Yeah, that's the answer.
Good.
Okay. I see. I was when I looked at this answer first, I was still in the math 200 mindset, looking at these like the equipotentials as like a topographic map.
Yeah, and there's nothing wrong with that. That's exactly what we're doing.
Like for part A, it asks what does it ask for? It's is the magnitude of the field larger at A or B? And I put A because they were closer together, the lines.
Yeah. And I actually calculated at A, but an easier answer is just because they're closer together, the voltage change per distance would be bigger because it's a shorter distance.
Yeah.
You know, the 4 volts, we only had to go 1 centimeter to change by 4 volts, where in B, to change by 4 volts, we had to go 2 centimeters.
Mm-hmm.
Yeah, and then of course we're doing our equipotentials are electric potentials. Contour maps, well, I guess contour maps don't have to be gravity contour maps, but they usually are.
Yeah.
Yeah, and so, so this could be a map of the equipotentials for gravity.
Mm-hmm.
You know, the contours of the same altitude for gravity. Sure. And then the closer, but it's the same that you're learning in your math class. The closer they are together, the bigger the gradient is.
Yeah. Right. Yeah, that makes, see that equation now, the delta V over delta S makes much more sense now. Voltage over the distance.
Oh, good. Now I see there's a C, but it looks like I did the C. It says draw the field. Okay, yeah. So I kind of did that at the first.
Yeah, I just did that the same way I would do it when I took Math 200 over the summer.
Okay. And did they have you? They have you draw the vector field perpendicular?
Yeah. Yeah, I just drew the vector fields perpendicular to the equipotential line.
Yeah. So good. Although, this class is taught with the idea that you don't necessarily need to have done Math 200. So
Yeah.
one of the things that the author was saying when they wrote, maybe I'll put this equation here, but the delta V, so the change in the equipotentials, is equal to negative, and there's an integral. And the real key is the dot product here. And that dot product is telling us then that the equipotentials, the contour of the same voltage, must be at 90 degrees to the electric field, because that's how you would get zero. The dot product would be cosine of 90 degrees. So in your case, you've had some experience with this outside of this class, but for most people, they have to see this dot product to realize that the field is going to be perpendicular to the equipotentials. But
Yeah.
and since it's new, hopefully I said that in the lecture, and I think I said that in the lab too, at the getting started in the lab.
Okay. Oh yeah, I got a couple more minutes. Could we do 29 part B?
Sure, 29. Part B. Okay. I'm gonna switch back over to the camera for this one. Okay, learning, share. Oh yeah, the share goes to the top of the screen when I do that. Share, come back over here. The camera, and then I gotta turn on the screen sharing. That's probably the only bummer thing about going to back and forth is gotta switch over. And let me get this into focus. Nice. And I'll cross this out because now we are doing chapter 25, number 29. I'll put it in my notes here so that I have that. I can try to remember to add that to the description. Okay, here. So here it says the potential in the region between 0 and 6 meters is given by, and so they have the potential equals to A plus BX. And then they give A as 10, B as -7. Determine A, the potential at 0 and 3. I'll put that in just for completeness. I know you asked about B. So, but this is just, as you pointed out, a plug and chug. So I'll just put it in. I won't even calculate it. So that's a 10. The B is a -7. And then you would put 0 for one of them. And the other one, you'd put a 10. And then plus a -7 for B. And then you put a 3 there. Actually, I might as well do them. So that comes out to be a 10. And then this is -21. Plus 10, so that's a -11. All right, so that's A, but you're asking about B, so and you're shaking your head like, yeah, okay, I know that one.
I did manage to do part A.
Now, here's the part that I don't know if you did caught this or not, but it says, find the magnitude and the direction of the electric field. So one of the conclusions we can write from this equation, besides the one we just talked about in the last problem, this equation would tell us that the equipotentials are perpendicular to the electric field. But they would also tell us that if you wanted to get, say, the electric field in the x direction, you have to undo that integral. So you have to take the derivative of the potential with respect to x with a negative sign, if I brought the negative to the other side, to get the electric field in the x direction. Likewise, to get the electric field in the y direction, you would have to take the derivative of the potential with respect to y. Okay, so this problem is asking for the magnitude and the direction. So I'll just do the components, and that will give me the magnitude and the direction. So if I come back up here to this equation and I take its derivative with a negative in front of it, the derivative of A is 0. The derivative of bx is just b. That's the derivative. Put a negative in front of it. And so that is a negative b, which b,
7.
is a, and that b is a negative 7. So the two negatives together make a positive 7. And I should put the unit volt per meter. So that's the electric field in the x direction, and kind of the boring derivative, since there are no y's in here, we did say, well, that's got no y, that's got no y. So the derivative of the first one would be 0. The derivative of the next one would be 0. And so the electric field would be 0. So if I wrote it as a vector, I would say the electric field then is 7 volts per meter in the I hat direction and 0 in the J hat direction, which usually we don't even bother to write that. So there is the magnitude 7, and the direction is the positive x direction.
Okay. So when you're solving for EX, the electric field in the x direction, that is the derivative of the potential in terms of x.
Yes.
Okay.
And I'll even scroll down here because I think you're asked to do that. This is the first time in a problem, but I think, look at the next one. The next one has a potential that's much more complicated, but it's the same logic. You're going to be taking the derivatives with respect to x and then respect to y, and then respect to z to get the x, y, and z components.
Was there I have that problem marked. Let me see why. I think I figured that one out. Yeah. Okay.
Oh, good.
It's interesting. I have it marked down as a problem I needed to ask, but I think I figured it out. I think I see at that point I didn't know about the derivative, taking the derivative, and so when I saw that function 5x minus 3x squared y, I just tried it. I just did it. I just did a derivative in the x, and then I looked at the solution page, it was right, and I was like, oh, okay.
Okay, well, that's what the learning process is. But I would say something inside of you, your gut was telling you to do that.
Yeah.
It could have been from the reading on this class, but it could have also been from your Math 200, because now in Math 200, you would have used a fancier word and said, take the gradient of it.
Yeah.
But the gradient, of the equipotentials, it really is the 3 components, right? You take, So anyways, so your gut was right, and now you're kind of putting it into words, I think, now that you've heard me say it. Mm-hmm.
Yeah. Well, I think that's it for right now. I'm going to continue doing these problems because I'm almost done with the section, but I know the last 2 or 3 are very hard with your lecture so often. Number 63, 62, and 63 are not easy, I think.